Okay, good afternoon, everybody. Welcome to today's TSVP talk. It is my great pleasure to introduce today's speaker, Will Horowitz. Will is an associate professor at the University of Cape Town. He received his PhD in physics from Columbia University in 2008. After a postdoc position at Ohio State University, he moved to the University of Cape Town in 2010. Since arriving at UCT, Will has won several awards. He founded a Society of Physics Students at UCT, established the SA CERN Excellence Bursaries, and created and directs the South African Theory and Computational School, which is the first semi-virtual postgraduate level teaching platform in physics and mathematics in South Africa. Will's research interests are in quantum field theory, string theory, numerical methods, and the foundations of classical and quantum mechanics. So today he will talk about mathematics of physics at 1 trillion degrees.
Super, thank you so much. Thank you for introducing me. Thank TSVP for hosting me and OIST for hosting me. It's fantastic to be here. So I have a couple of, so this is an outreach talk, general interest talk. So I have a couple of nice little demonstrations that I'll pass around. The first here is in this cup. With some oobleck, which is a non-Newtonian fluid, and we'll talk a bit more about that later. So just make sure that you really jab the stuff to notice how the viscosity increases, and then let the spoon move slowly and see how much easier it is to move the spoon through the fluid. And the second object is a piece of scintillator, which I'll talk more about later. But what you should notice, if you can, it's actually an impressive display of the quality of glass that you have on the building in terms of blocking out UV light. But what happens is high energy particles, photons being one of them, go through the scintillator to excite the material, and the material de-excites and emits light in a bit of a purple color. I found that if I turn this sort of a odd direction, I can see the purple on the edge. You'll notice it then. And then we can talk more about that later. So just please pass that around. Okay, great. So, want to talk about the mathematics of the physics of 1 trillion degrees. And this is based on some recent work that we posted on the archive in terms of the physics of 1 trillion degrees. And then this is a bit of an interesting talk where I wanted to do both a general interest talk, but also try to cater to the more mathematical folks. So if I'm successful, everybody will be happy. And hopefully I'll avoid the problem that happens when you try to do 2 or more things at once, which is that nobody's happy. Okay, great. So let me give you a sense of what we're going to do. So we're going to talk about physics of 1 trillion degrees. So why we're interested, how we study this thing, and then things that we're doing in the future. And then we'll talk about the exact symmetry preservation in numerical solutions to PDEs. This is the more mathy technical side. And then I'm sure we will not have time to talk about this. We'll talk about denominator regularization and quantum field theories. This is super technical. And what I want to say is please stop me at any time. I believe that I've made the talk at a level where certainly the talk in terms of the physics of 1 trillion degrees, everybody should understand. But it's very easy for somebody who's been in a field for 20 plus years to slip into jargon and forget that you haven't also been in the field for 20 years. So just please, as I said, stop me at any time. Okay, so the first thing that I want to do is remind us about ideas about many-body physics. And in particular, the phase diagram that we're most used to is the phase diagram for water. And the idea is that we're going from the physics of a few to the physics of many. And what does it mean to have the physics of the many? And it means that you're not necessarily interested in the particular locations and trajectories of individual particles, but about the properties of some substance as a whole. And here we have the phase diagram of water. So on the y-axis, we plot pressure, and on the x-axis, we plot temperature. And we have different phases. This is the cartoon phase diagram of water that we all see in chemistry in high school. And at low temperatures, we have the solid phase where we have ice. And then as we rise in temperature for reasonable pressures, we will undergo a phase transition to a liquid. And if we continue to raise the temperature, we'll go through another phase transition, we'll end up as a gas. And there are several interesting aspects about this that I think I certainly didn't appreciate when I was in high school chemistry. So first of all, what does it even mean to be a solid or a liquid or a gas? And it's really just a collection of properties, right? So a solid is something which is incompressible and maintains its shape. A liquid is incompressible but takes the shape of its container, and then a gas is compressible and takes the shape of its container. Okay, super. Now, what's also really interesting about this phase diagram is that these phase transitions are what is known as first order. In our everyday life, we tend to experience the world as being continuous. You make a little bit of a change here, your output has a little bit of a change. A discontinuity is where you make a little change and you get a very big change in the result. And if you think about the phase diagram of water, what's wild is that as I change the temperature, say I have ice and it's at -20 Celsius, as I raise the temperature up towards 0 degrees Celsius at standard pressure, the properties of the ice don't change, roughly speaking. It stays exactly the same. And it's really right at 0 degrees Celsius that something dramatic really happens, which is where it changes from a solid to a liquid. And the same thing happens at the liquid to gas phase transition, that this is a first order phase transition. And it's as I said, it's wild that that happens. And it's interesting that if we look at another common substance, say butter, butter has the properties where you have the continuous phase transition that we would expect with what we usually experience in the everyday world. I take butter out of the fridge, it's very much a solid, it's incompressible, it can't be molded. But as it warms up, it becomes malleable. And then as I put it in the pan, it then melts. And it's a smooth transition from the properties that we expect of a solid to the properties we expect of a liquid. And you could think about not just water, which is obviously the most important substance on Earth, or butter, which is the most important substance in pastry baking. But you could ask, well, what are the properties of the entire universe, right? Can we think about the universe as a substance and what kind of fluid-like properties the universe has? Or we could think about our oobleck here, which is a non-Newtonian fluid. So we could think about the viscosity of this material, how the viscosity changes with shear. So that's what I want you to think about. And I also want you to think about, as we'll talk about more later, is how much stuff do I need to have a sensible idea about a phase? So I have a cup of oobleck. I can take half that cup of oobleck. It's still going to be oobleck. I can keep doing the Zeno-type thought experiment. I half and half and half and half. How small can I get of a droplet of oobleck and still have this idea of viscosity, temperature, pressure? All right, great. So in particular, what I study and what my group studies is the phase diagram of QCD. And we're interested in what we call the emergent many-body properties of the strong force, which is nuclear matter. So instead of pressure and temperature, I'm going to have temperature on the y-axis and what's known as baryon chemical potential on the x-axis. So baryon chemical potential is basically how hard it is to put a neutron into the system. So normal nuclear matter here, this is us. If I increase the baryon chemical potential to a very high amount, it's the center of neutron stars. If I go to very high temperatures and very low baryon chemical potential, this is the early universe. In the center of neutron stars, we think there's a phase transition. We think that nuclear matter becomes superconducting, just like superconducting electromagnetic material, but for colored matter, QCD matter. And then at very high temperature and low baryon chemical potential, we think that the universe was in a quark gluon plasma. So the normal nuclear matter that we're made out of protons and neutrons, the fundamental degrees of freedom are quarks and gluons. And the idea is at very high temperature, we release those fundamental degrees of freedom and the properties change dramatically. And what we'd like to do is we'd like to explore at this very high temperature, very low baryon density, theoretically and experimentally the properties of nuclear matter. My group focuses on the theoretical aspect. Okay, so if any of that was not necessarily well understood, we're going to go and talk about it in detail, reverse order. Okay, great. So what are the forces? So we've got gravity, electromagnetism, the weak force and the strong force. We're used to gravity. We're used to electromagnetism. shocking ourselves in the socket. The weak force, roughly speaking, breaks nuclei apart, and the strong force, roughly speaking, keeps nuclei together. Nuclei are made up of protons and neutrons. The protons and neutrons are made up of quarks and gluons. And quarks and gluons are analogous to electrons and photons for the electromagnetic force. And under normal conditions that we experience on Earth, the quarks and gluons are confined inside of the nucleus. The strong force in general is described by a quantum field theory. So quantum field theory, we know that the physics of the very small quantum mechanics, the physics of the very fast of special relativity. When you have those two together, it's a quantum field theory. Electromagnetism is described by quantum electrodynamics. The strong force is described by quantum chromodynamics. So instead of just a plus minus charge, we have 3 color charges. When QCD was first being explored, the Americans wanted the 3 colors to be red, white, and blue. But reason prevailed, and the 3 colors are red, green, and blue, and you put the 3 colors together for a color-neutral white object. QCD is an extremely complicated theory, and there are many open problems even today. For example, where does mass emerge in quantum chromodynamics? Why does the proton have a typical mass of 1 GeV? And for example, if you prove that there's a mass gap rigorously in a non-abelian quantum field theory, you'll win a $1 million Clay Prize. Sadly, due to inflation, $1 million doesn't get you nearly as far as it did back in 2000. Okay, so the strong force is just a very interesting theory to think about. And we want to think about not just about the strong force in terms of particle physics, but in terms of many-body physics. So what does that mean? So if you do first-year physics in college, what you're really doing is particle physics. You're asking, I have some particle that has some initial position and some initial velocity. What is the motion of that particle as a function of time? And if I'm, for example, in gravity, I get some parabolic trajectory. And this can be seen in nature, for example, somebody who decides to be crazy and jump off a cliff, and you see the parabolic motion there precisely. And this is also true for charged matter. So for example, if I have some charged particle in electric or in a magnetic field, then there's some helical motion. And we can see this explicitly in the Northern Lights, for example. All right. Now, how does our extremely precise, extremely good understanding of particle physics, of the dynamics of a single particle, manifest then into the properties when we get a lot of that matter together? So for example, how do the fundamental equations of electromagnetism, Maxwell's equations, and quantum mechanics lead to the properties of water? Because a single H2O molecule is very boring. It vibrates, it rotates. It's very, very well understood. But this is the real phase diagram of water. What I showed you before was the cartoon picture from high school. I still have pressure on the y-axis. I still have temperature on the x-axis. I still have solid, liquid, and gas. But even within solids, there are many different phases. The bulk properties of the solid do change. So it's still incompressible, still keeps its own shape. But say the conductivity of the matter changes, or the crystalline structure of the matter changes. And this very complicated structure, even qualitatively, has never been described starting from Maxwell's equations in quantum mechanics. It's an unbelievably difficult problem. And even though we're starting from very simple rules. Okay, good. Now, this emergent behavior, where now you have phases, and you have, instead of describing the individual locations of particles and their velocities, we now start talking about collective behavior. What is the pressure, the temperature, the compressibility? Do waves form in this substance? And this emergence is actually everywhere. For example, I went to Georgia Tech in undergrad, and one of the professors there recently asked, okay, well, let's just create a 2D distribution of ants, And can we think about this 2D distribution of ants as a liquid? Does it have properties that we expect of a liquid? And sure enough, if you drop a penny, which is you can't do anymore because they don't print them anymore, but if you drop a penny into a distribution of ants, you can measure how quickly the penny drops. And therefore, you can experimentally measure the viscosity of ants. We like to think of ourselves as individuals, individual snowflakes, perfect little things. But you put a lot of us together, a lot of humans together, we start to develop collective behavior. So here's an Oasis concert in the UK, and you can see a wave propagating amongst the humans. So a wave through the human medium. You see this wave propagating. And what I love about this, not only is there a collective behavior amongst the humans, but even the wave of humans tunnels, just like in quantum mechanics, right? So you watch the wave propagate through the humans, and then watch as the wave propagates not through the humans, and there's a gap of humans, and then there's the security guards, and then all the security guards then move back. All right, great. And deeply important fundamental question. We have 10 to the 11 neurons in our brain. How does that lead to consciousness? Consciousness being this emergent phenomenon that comes from the fact that there are just a lot of neurons up here. So all of these things are emergent phenomena because we have many objects all together. Okay, so this is a technically detailed slide. The point that I want you to take away is that the lines go through the dots. And the lines going through the dots tell us that the particle physics of the strong force, where the individual quarks and gluons are, that's well understood. And so what we'd like to do now, just like with humans, or just like with the phase diagram for water, we would like to explore in detail the phase diagram of the strong force. And you might be asking yourself, well, geez, electromagnetism plus quantum mechanics, we can't get water. Why would there be any hope of exploring what seems to be an even more complicated theory in the phase diagram of that more complicated theory? And the answer is several-fold. One is that, well, and basically, there are several reasons which boil down to there are reasons to believe that the strong force may be simpler in certain ways than, for example, water. So water has a number of different scales involved, and that always makes things very difficult. But also the fact that quantum chromodynamics, technically it's known as a non-abelian quantum field theory, and electromagnetism is known as a abelian field theory. Non-abelian basically means hard, usually, but might in some senses make the system easier to think about. And in any case, the fact that we're exploring this phase diagram is all about attacking the problem from a different direction. And maybe we can gain some interesting insight that might be applicable elsewhere, in addition to just learning fundamentally about the strong nuclear force. Okay, speaking of, so why care? Well, what are ultimately the unchanging physical laws of the universe? So I think we all want to make some kind of fundamental impact on the world, and being able to describe the properties of some substance in the world of fundamental nature is of inherent value.
So what was that library? Where is it?
I think it's in Spain. Yeah, it's a good question. So you want to visit, eh?
It says OIST.
All of my slides say OIST. All right, what else? Okay, so is there a most perfect liquid? So coming back to our oobleck, so I've mentioned viscosity a couple of times. So what is viscosity? Roughly speaking, we know in our everyday world, when we're not dealing with fluids, that friction is a dissipative process. And viscosity in fluids is like the friction for fluids. And if I plot here temperature, and really the difference in temperature between the critical temperature for a phase transition and the temperature, and I plot on the y-axis the shear viscosity to entropy density ratio. This is the unitless quantity, the unitless ratio that tells you about your deviations away from perfect fluidity. And I look at a number of different fluids. Most importantly, water, for example, here, but also superfluid helium. you'll see that water, which we would think of nominally as a pretty darn good fluid, this dimensionless ratio 8/s is somewhere between 2 and 3, and we would want it to be much, much less than 1. Much, much less than 1 says you're a very good fluid. Superfluid helium is only a little bit below 1. When we've examined the properties of nuclear matter at very low temperature, very low baryon chemical potential and very high temperature around the phase transition to what we call quark-gluon plasma, it turns out that this shear viscosity to entropy density ratio is very small, about 0.1. And there's a question, is there a lower limit here? So I can certainly write 8/s is just 0, but is there any matter in the world that can get to 0? And there are very good reasons to believe that no, you can't, actually. That there are ideas from string theory as applied to the natural world that say that fundamentally you can only get to 1/4 pi for an infinitely strongly coupled theory. So you think that if the theory is if the particles interact with each other very strongly, then you're going to get very close to a perfect fluid. And even if you have an infinite coupling, you can only get to 1/4 pi, which is about 0.08. You might also think that just Heisenberg uncertainty from quantum mechanics places a certain restriction on how perfect you can be. This is the inherent fuzziness of the natural world. I also talked about the universe. We know that the universe has a temperature. Now, about 14 billion years after the Big Bang, the universe is a couple of Kelvin. As we go back in time, the universe gets hotter and hotter. About 300,000 years after the Big Bang, the universe was so hot that hydrogen couldn't even exist. And when hydrogen can't exist, light can't propagate through the universe. So we know that when we look out at the night sky, we're looking back in time, that the light emitted from stars came from millions of years ago. And so you would think, oh, if I just look far enough away into the universe, I can look all the way back to the Big Bang. That's not true. There's a fundamental limitation to how far back we can look in time as we look out into the universe using electromagnetic probes. And that limit, this fundamental limit, is about 300,000 years after the Big Bang. So if we would like to understand, if we'd like to probe the properties of the universe even earlier in time, we have to use some other tool. And it turns out that about a microsecond after the Big Bang, the whole universe was at 1 trillion degrees, and the universe went through a phase transition, this phase transition that I've been talking about, from quark and gluon degrees of freedom to normal nuclear matter. And so as we explore the phase diagram of the strong force, we are exploring the fundamental properties of the universe a microsecond after the Big Bang. And this is the farthest back in time we as a species can look in terms of the properties of the universe. There are also connections to other fields. So many people think that at the temperatures that are explored at colliders such as the Large Hadron Collider, the temperature is enormous. It's 1 trillion degrees, but it's not so hot that the physics is weakly coupled. There is a suggestion, or there are many reasons to believe that the physics is strongly coupled. And there are other interesting types of physics where the physics is expected to be strongly coupled. In particular, high temperature superconductivity is believed to be dominated by or described by strongly coupled dynamics. And there are very few theoretical tools for exploring quantitative or even qualitatively strongly coupled dynamics. So it might be that, and it has been the case, that the tools that have been developed to study this part of the phase diagram of the strong force have now been used to study the dynamics of high temperature superconductors. Then, as I mentioned also earlier, there's a question of how much is enough? So how many particles are needed for something to be considered a phase of matter? And here we have a connection between cold atoms and hot QCD. So here on the left-hand side, directly motivated by the physics of quark-gluon plasma, people were looking at lithium-6 ions and trying to understand how many lithium-6 ions you need for collective behavior to emerge. And if you've taken a statistical mechanics course, you'd say, oh, well, I need a mole's worth of stuff to be macroscopic. Like that's literally what a mole means. How many things do I need to be macroscopic? So it's 6.022 times 10 to the 23 things. When we were looking at heavy ion collisions, as I'll talk about in a moment, exploring the physics of the phase diagram of nuclear matter, early days, people were seeing 15,000 particles. And for 15,000 particles, they're seeing collective behavior. And we thought, that seems pretty reasonable. 1 over the square root of 15,000 is a pretty small number. Now, in the last 10 years, the number of particles needed within the nuclear physics community to see collective behavior is getting smaller and smaller. It's from 15,000 to 150 to 100 to maybe 50. From the cold atom side, here we've got the atomic number, or the number, not the atomic number, sorry, the number of atoms. So I have 2 lithium atoms here, and I see a consistency between a non-interacting theory where obviously nothing is going to happen versus a strongly interacting theory. The 2 give the same result. If I look at 4 atoms, so 2 up lithium atoms, 2 down lithium atoms, again, the non-interacting theory and the interacting theory agree. 6, 3 up, 3 down, non-interacting theory looks isotropic, nothing interesting happening, no collective behavior emerging. But if I have interactions, then collective behavior appears to emerge. So we've gone from 6.022 times 10 to the 23 particles needed for collective behavior to 6, a drop of 23 orders of magnitude. And this is really a fundamental question of importance in physics that we are currently exploring. How many is enough? So here, this is the most recent work that my group has done. And lots of details, but what I want you to really focus on is on the top plot. And I want you to compare, actually, interestingly enough, the uninteresting blue physics versus the interesting red physics. And here, this is the number of nuclei involved, or sorry, the number of nucleons in a nucleus. So here we have 2 lead nuclei colliding. Here we have 2 gold nuclei colliding. So we're going down in the number of things. And then here we have neon and oxygen, and there's clearly they're well separated. And so you can experimentally hope to see a difference between the physics, the boring physics and the interesting physics. And that was done very recently in the last summer at the Large Hadron Collider. And it turns out that it seems like there's hope to even collide lithium nuclei. Again, with lithium, just sort of a random coincidence, that we can get down to colliding lithium nuclei and hope to see some interesting collective behavior. Okay, so that's a good introduction. So how might we explore the phase diagram of nuclear matter? We spend a lot of money, spend a few $1 billion and build the relativistic heavy ion collider at Brookhaven National Lab in Long Island, New York, a few hours outside of New York City, and collide gold nuclei. Or you can use the Large Hadron Collider at CERN. Large Hadron Collider, main purpose was built to discover the Higgs, but also from the very beginning, there was a heavy ion physics program. And in particular, there's a dedicated heavy ion physics detector, the OIST detector here, which is based here. And to give you a sense of the scale, that's the Geneva International Airport. And it crosses the border, and so mercifully, the colliding particles don't need to show their passport. Thank you, Schengen Agreement. And to give you a sense of scale, so there are about 10 to the 10 or 10 to the 11, say, lead nuclei that circulate in the Large Hadron Collider at any one time. So it's about 10 to the minus 12 grams. But the amount of kinetic energy stored in the ring is that of an A380 taxiing down a runway. So one of those double-decker planes. And when the 2 nuclei collide, just the one nucleus and another nucleus, the amount of kinetic energy that's involved is about the same as 2 mosquitoes colliding in midair. It's really macroscopic quantities of energy that's involved. Also, potentially very importantly, CERN is a public lab, publicly funded, so outreach is very important to them. If you're ever in Europe now, so the Large Hadron Collider is shut down for the next several years for repairs, basically the machine has burned itself out from radiation, you can go and visit, and you can go in the tunnel, and you can see the magnets, but most importantly, you can see the detectors, and they're enormous. They're the most complicated devices ever created by us as a species. It's really worth your time. And if you want, send me an email, and I can put you in touch with a good tour guide. Yeah. All right. So to give you a sense, here's the Atlas detector under construction. That's a human. And this is the CMS detector. Again, there's a human for scale. And there's nothing, you can conceptualize it by seeing this, but nothing compares to actually being there in person. Here's an event display from the OIST detector. So you get, as I mentioned, 15,000 particles emerging at a time. And what's amazing is that you can get usable information out of this. So the simplest thing you could ask is there a temperature? And I can go into details about how you measure the temperature, but you can measure the temperature. And the temperature, as mentioned, is 1 trillion degrees. And somebody actually went through the process of having this certified by the Guinness Book of World Records. It's the hottest temperature ever observed. And it's also the hottest temperature ever obviously created. And we as a species created. And I think that's always worth taking a moment to reflect on. You know, it's sort of obvious when people get launched into space, that's incredible. People go to the bottom of the ocean, that's incredible. But we're also doing incredible things in terms of science, in terms of creating objects that are at 1 trillion degrees. How hot is 1 trillion degrees? It's literally 100,000 times hotter than the center of the sun.
Because how large is the volume in which you had this temperature? Like a fist or much smaller?
It's a fist. So it starts off on nuclear scales. So the scale to have in mind is that a proton is a femtometer across, so 10 to the minus 15 meters. And then if you have a large nucleus like lead, the radius is about 6 femtometers. So say it's going to start off as something like 10 femtometers across, and it lasts for about 10 femtometers. So in natural units.
So that seems to blast the concept of temperature. I mean, if it's so small, it can't be an average kinetic energy or anything like that. So.
This is exactly it. I mean, isn't that wild, right? That you can think about something that's so unbelievably small, and yet a temperature is very much well defined. So I know you're a physicist, so I'm going to talk a little bit technically, but you know that just from the Boltzmann distribution, e to the minus mass over temperature, e to the minus energy over temperature, energy being mass in this case. And you can just look at the distribution of the number of particles as a function of particle species, which is to say mass. And you see just this unbelievable across, what is this, 7 orders of magnitude. Very good agreement in the distribution of these different particle species based purely on a single temperature. So temperature really is a very good descriptor of this medium that is created in heavy ion collisions, this collective properties that we associate with phases of matter on macroscopic scales with a mole's worth of stuff can really be used to describe matter that is on the femtometer scale and only, in this case, a few thousand particles.
So we'll maybe then.
Yeah.
When you talk about the temperature universe, after just a microsecond, how big was the universe at that time?
I can't say. It's also a bit technical. Maybe let's chat after about that.
Yeah, but not much smaller than we think about the universe today, right? Or is it?
Oh yeah, definitely. No. But it's also not entirely clear.
Mm-hmm.
All right. So let me maybe coming back to the skepticism of temperature, well-founded skepticism of temperature. Let's talk about another aspect where we see collective motion, or reason to believe there's collective behavior happening in these incredibly small systems. So these 2 nuclei, they're roughly spherical. They are Lorentz boosted to pancakes, so they look like little circles. So I have one circle and another circle that are colliding into each other. And the overlap is some kind of, roughly speaking, oval shape. So I have a geometric anisotropy in my system at the initial time. Now, if there's collective behavior, if I have a fluid with pressure. I have pressure gradients that develop as a result of the geometric anisotropy. And in particular, I have larger spatial gradients in the short direction than in the long direction. And so I expect there to be larger pressure gradients, larger pressure in the short direction versus the long direction. So the system will preferentially blow out in the short physical spatial direction, and I'll have greater momentum in that x direction than in the y direction. And what one can do is one can quantitatively, using relativistic viscous hydrodynamics, and I'll show you in a few plots or a few slides later, one can quantitatively predict this distribution of matter in momentum space and compare it to data, and being extraordinarily good quantitative agreement. And we can make a connection, again, back to space science, where there is some initial anisotropy in the temperature distribution of the universe. And those anisotropies, through time, imprint themselves on the mass distribution of the universe, with clustering of galaxies and basically the mass distribution. And one can look at those fluctuations and do a decomposition and understand in detail the initial fluctuations of the universe. And in exactly the same way, when these two nuclei collide, there are quantum fluctuations in the initial nuclear wave function that imprint themselves on the initial energy density profile, which is propagated to final times through relativistic viscous hydrodynamics. This is an old set of plots, but it demonstrates the point, which is if I try to characterize this distribution of particles in the azimuthal plane, I'm going to use a Fourier decomposition. And the most important Fourier component is what we call a V2. And that's plotted, for example, here on the y-axis as a function of what's known as centrality, so how much these two nuclei overlap. And what you can do is you can take your simulation and you can use as a knob the shear viscosity to entropy density ratio here. And you can compare your curves to data, and you see that the predictions are in very, very good agreement with the data, giving you a sense of how perfect the fluid is, how small this 8/s is, which is what I mentioned earlier. Another thing that can happen when you have these two nuclei going past each other at this, roughly speaking, the speed of light, you will find that, or you expect then, that the material, the medium, to be spinning. And if the medium has very, very little viscosity, then these vortices will imprint themselves on the polarization of certain particles that emerge from the medium. And you can measure that. And what one finds is that the angular frequency of this quark-gluon plasma is on the order of 10 to the 22 radians per second. How big is that? Well, tornadoes are about 1/10 of a radian per second. And the fastest rotating material we've ever seen before this was superfluid nanodroplets, which had about 10 to the 7 radians per second. So it's 15 orders of magnitude larger. Now, you might ask, how much does the system rotate? And coming back to the scales, so everything is femtometer scales. So things last for about 10 femtometers, 10 to the minus 14 meters. I include the speed of light, 10 to the 8 meters per second. So I get about 10 to the minus 22 seconds. So even though this system is rotating with an unbelievably fast angular velocity, it makes about 15 degrees of rotation before the system falls apart. This formed the cover of Nature a few years ago. Okay, great. And also, because I have two large nuclei going past each other, they have very large positive charge, they're moving, and so there's an enormous magnetic field. So the prediction is that the magnetic field created is about 10 to the 15 Tesla, which is enormous compared to any other object in the universe. Okay, I see I've been talking for a long time. So let me maybe speed things up to get to at least the end of the public interest part of the talk. And then maybe we'll do the more mathy thing in a more dedicated session. So we go to small systems. How much do you need? And the point that I just want to make with these plots is just that the signs that we expect for a new phase of matter that have been observed in large nuclei collisions are also seen in small collisions. In particular, here we're looking at the number of particles that are measured in the final state, so 1,000 to 110. And you'll see that there's a continuous trend amongst the data. You wouldn't be able to tell whether the system was physically small in terms of a proton on proton collision, a proton on lead collision, or a lead on lead collision. The observable seems to depend only on the number of things, and there's a smooth transition. And here's another example of viscous relativistic hydrodynamics calculation. And you see, say, comparing the red to the red, across all these various systems, there's extraordinarily good agreement. Okay. Yes, good. So how might we do calculations? Because we want to, from the theoretical side, understand the properties that we're observing. So the tools that we have are actually very, very limited. The first tool is that of perturbative quantum field theory. So these are Feynman diagrams. And again, this plot is just meant to indicate that the lines go through the points. You're able to compute any quantity of interest, but you're restricted to small coupling, which says you need some kind of a large scale, very high momentum. Another method I've referred to is what's known as the ADS-CFT conjecture or the Maldacena conjecture. This is ADS-CFT duality, which says that you can think about either your quantum field theory in 4 dimensions or a string theory in 5 dimensions. And the string theory miraculously is weakly coupled when the field theory is strongly coupled. And weakly coupled string theory is just gravity. So it's Einstein general relativity. You can, again, compute more or less anything that you want, but it's complicated for several reasons. One is that the theory here is not quite QCD. So it's not entirely clear how good of an approximation this is. And then to motivate the exact symmetry preservation discussion that I'm just going to go over very quickly, you might think, oh, let's just put everything on a computer. It's a hard problem, but we have a lot of money. We have big computers. At least before NVIDIA and all the data centers took it up for all the computing power for AI, you could go to national labs and ask for computing time. And you would discretize all of space and time, and you would put the QCD Lagrangian on that, and you could compute quantities with very good precision and describe data very well. And in particular here, I'm looking at the entropy density divided by temperature cubed as a function of temperature. And what you see, which in this entropy is basically counting for you the degrees of freedom. And so you see with normal nuclear matter, the degrees of freedom are basically pions, normal nuclear matter. And then at some temperature, something dramatic happens. You're releasing a huge number of degrees of freedom. But the problem, there are several fundamental issues with just putting everything on a computer. One is that you're restricted to what is known as Euclidean correlators. So if you try to ask questions about real-time dynamics, what happens as a particle propagates through this medium, for example, then if you try to put this on a computer, you have what's known as the sign problem. But what that really means is you're basically trying to integrate a highly oscillating function. That's just technically not possible. So you're restricted to asking questions about pressure, entropy, equation of state. Another problem is that you've really fundamentally violated some important principles in terms of conservation. Not in terms of, well, yes, in terms of conservation, but in terms of symmetry. That the natural world, as far as we understand it, is not discretized. There are these continuous symmetries. And why is that important? From a fundamental physics perspective, symmetries are fundamental. they tell us how to think about the universe. From an everyday point of view, we know the imprint of symmetries because symmetries lead through Noether lead to conservation laws. So if you have translational symmetry of conservation of momentum, if you have rotational symmetry of conservation of angular momentum, time translation symmetry of conservation of energy. For example, if you have a U1 gauge symmetry, then you have a conservation of charge. And you saw very nicely this, we have the Winter Olympics happening right now. And if I can find my cursor, then yes, we can see what happens as this person decreases their moment of inertia. The angular momentum has to remain the same, so her angular frequency increases. But this fundamental sticking point in terms of lattice QCD trying to put quantum chromodynamics on a computer is that the fundamental laws of quantum mechanics through, say, Wigner's program tell us that the particles that are allowed in our universe are dictated completely by the symmetries of the universe. And this is incredibly profound. The objects that we see around us, electrons, photons, say the Higgs particle, are really the only objects we can have just due to the Poincare symmetry of the universe. That we have translational invariance, we have rotational invariance, we have Lorentz boost invariance. And as soon as we discretize our space-time, when we're trying to solve something numerically, we're fundamentally breaking all of those continuous symmetries. And the way that that imprints itself in a lattice QCD calculation is that your particle content of your universe is not the particle content of our universe. For example, you have the fermion doubling problem. And for many problems in numerical calculations, you have a smooth, a continuous convergence to the continuum limit as you take the spacing to zero. But this breaking of continuous symmetries is discontinuous. There's no spacing that's small enough in the discrete limit to lead to the continuous limit. And so we are interested, certainly from the fundamental perspective, of exactly preserving symmetries, even in numerical simulations. Now, if we go to practical applications, which I'm less familiar with, which is part of why I'm actually visiting OIST, is to understand ways in which this breaking of continuous symmetries is important for practical applications. So, for example, if we look at the discretization of time, when you numerically solve, say, PDEs, you're going to be breaking time translation invariance, continuous time translation invariance. So you break the conservation of energy. That manifests, for example, in an energy drift when you're solving, say, the inviscid-Euler equations, which shouldn't be dissipative. This is also important in terms of looking at the stability of your numerical solver. If you break your rotational invariance, you have preferred grid directions. You also have symmetry breaking noise. This can lead to anisotropic viscosity and an incorrect energy spectrum in your turbulent flows. And turbulence is a very important problem in many different applications. So here we have turbulent flow caused by the presence of a cylinder in the flow of a gas. And here is a numerical simulation of that. All right, so we don't want to break symmetries. What we want to do is we want to write down our physics in terms of quantities that are reparameterization invariant, technically in action. And what we'd like to do here, we have the point particle action for a relativistic particle, where we take our parameter space is just some parameter we call tau, and we map that tau into a path through space and time, describing both the position and time of the particle. So treating time and position on equal footing. You can go to higher dimensional objects, and this is a classical string theory, where I take a two-dimensional plane, tau, which is kind of time-like, sigma, which is kind of space-like, and I map out a sheet through space and time. And what we're going to do, okay, well, I'll tell us what we're going to do in just a second. In terms of a point particle, what we're going to do is we're going to take a two-dimensional plane, tau, which is kind of time-like, sigma, which is kind of space-like, and I map out a sheet through space and time. And what we're going to do, okay, well, I'll tell us what we're going to do in just a second. In terms of a point particle, we take the relativistic point particle action and expand it, we see a 1/2. And this 1/2, we think maybe that indicates that if I have a half in the theory I'm considering, maybe there is a more invariant theory that I should rather be considering. And so what's a canonical problem in PDEs? Well, it's just a wave equation. And normally I think about having my space and time, and I discretize my space and time, asking questions about the wave on top of the space and time, and I find a non-conservation of, say, my energy because of the discretization process. But now what I'd like to do is rather think about a parameter space, tau and sigma, and think about dynamical coordinates x and t as a function of tau and sigma. And I think about my wave living on top of the t and x dynamical coordinates that are parameterized by tau and sigma. And now I'm going to discretize in a trivial way my tau and sigma unphysical parameter space, allow my coordinates x and t to be determined dynamically, as well as my field, and now I have exact symmetry preservation. All right, almost done. So I mentioned waves. So what we're going to do is we're going to have our action for our waves with a factor of 1/2, which we take as some hint that we're doing something. We can consider some more symmetric theory. We'll have our action for our coordinates. And so we're going to look at a total action, which involves the dynamics of our coordinates and the dynamics of our fields, which when we expand it to leading order gives us the physics, the original physics that we started with. And what you can see is here we're going to, as a first step, take that time is a function of tau and sigma, but we're going to choose a particular gauge choice, we call it, where x is just given by a sigma. And when we do that, then our time and our position develop in a natural way. And here we have an initial Gaussian wave that propagates and reflects through our numerical solution. What's amazing is that we get an automatic mesh refinement. So if we look at the tau derivative of time, so how quickly does time itself evolve, you can see that where the field is doing interesting things, like for example at the initial time, where the field is doing interesting things like reflecting, time in fact slows down. The time derivative decreases, the tau derivative of time decreases, and where boring things are happening, like in the middle, this time derivative is increasing, is positive. And as mentioned, we have 2 global accuracy of precision of our system for our calculation. Energy is exactly conserved. All right, so hopefully what I've convinced you of, because now I'm basically just down to time for Q&A, hopefully I've convinced you that QCD, many-body QCD, is a rich and interesting field with connections to many areas of physics. The quark gluon plasma that we're exploring is an emergent phenomenon. It's beyond the standard model. So part of beyond standard model physics is, oh, they're new particles, neutralinos, gluinos, blah, 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 blah. But just emergent phenomena in general is beyond the understanding of the Lagrangian of the fundamental particle physics of the universe. And heavy ion collisions is a field of superlatives. We're creating the hottest matter in the universe, most perfect fluid ever measured, largest magnetic fields ever produced. Of fundamental interest right now is how big is big enough? And this is the new frontier in heavy ion collisions. How are thermodynamics and other properties of the quark gluon plasma modified by the fact that we're in a small system? To what extent does it make sense to even talk about temperature, pressure, viscosity, so on and so forth? And how does it also translate into other fields of physics like cold atoms? And then I very quickly breeze through novel tools for numerical solutions of PDEs that explicitly maintain exact continuous symmetries. And we'd like in future to generalize our procedure so that we can see, for example, center of mass preservation or exact conservation of angular momentum. And then we'd also like to consider generalization of boundary value conditions. So in particular industrial applications, for example, you might be interested in wave propagation to boundaries which are not reflecting. Those waves just go out to infinity. But necessarily you putting your system on some finite-sized grid because we have finite amount of computing power, and you don't want those waves to reflect. And generally you're going to get reflections that are going to contaminate your solution. And by our thought is perhaps with these novel techniques that we've encountered to try to preserve exactly continuous symmetries, we might be able to tackle these boundary value problems. Thank you very much.
Any questions?
Thank you, Will. Great. I have a question about this concept. We talked about density, barons.
So density?
Density in the beginning there. With I mispronounced the name. Barons, or when you have these fundamental particles, how much energy?
Oh, baryons.
Baryons. Okay. That density.
Yes.
It sounded like the definition of capacity of sets in mathematics is not much. If you have a 1 voltage difference and you take a unit charge and take it from infinity and place it on the set, how much energy that will take.
This is my reminder to send an email to my group.
That was just the concept there of that you have the long axis.
Yes. Here is the cartoon version. Yes, exactly. So if I take a neutron from infinity and bring it into my system, how difficult is that process?
So that sounds like a definition of capacity in mathematics for sets.
I could be.
Yeah, okay.
I'm not trying to be dismissive. I don't know that concept.
Maybe I don't know. You know what I mean, right? Or, no, okay.
Okay, good. It's not just me. Thank you very much.
But it's a concept of potential theory.
It must be related because it is so it's baryon chemical potential,
Right.
And it's also very similar to the idea when you have, say, an electrostatic a collection of electrostatic charges,
Right.
and you bring in another electron from infinity.
Right.
Yeah, exactly.
It's the same. Yeah, it's the same. The background, I guess, for these concepts.
Exactly, and basically the idea is how difficult is it to do this thing, and in general there's something that's conserved, coming back again to continuous symmetries, and here you have a conservation law. You have a conservation of baryon number, and that is associated with this baryon chemical potential. Exactly the same way that you have a conservation of electric charge. The thing that's hard to often conceptualize is that for us, we're at very high energies often. And so we have E equals mc squared, so you can create matter. So when it comes to, say, the electromagnetic force, you might have one negative charge, a total of one negative charge, which is conserved. But you're not going to have necessarily one electron. You could have one electron or two electrons and a positron, or three electrons and two positrons. The concept of bringing in something from infinity becomes a little bit mushier in this case. But in general, it's as I mentioned, everything in physics is determined by symmetries, which then leads to conservation. And so then when you discretize, you're really screwing up something very fundamental.
Any questions?
Yeah, it may be too technical, but I think saying that the quark-gluon plasma is beyond the standard model physics sort of stretches the idea of emergence and beyond this. I think many physicists would see this as standard model physics in the same sense that hydrodynamics is still Newtonian physics. So what made you say that this is beyond? I mean, people think of supergravity as string theory and so on as beyond the standard model. So what made you claim this?
Good. Yeah. So I'm definitely saying, I'm not saying that something like quark-gluon plasma or hydrodynamics is involving new fundamental physics, new fundamental particles. It's really about the reconceptualization of how we describe matter. That if you want to describe water, you're going to fail if you start with Maxwell's equations in quantum mechanics. So in some sense, while the fundamental interactions are not beyond electromagnetism and quantum mechanics, the way that we are going to solve the problem, work on the problem, conceptualize the problem is fundamentally completely different. And in that sense, it's beyond the physics, and in that sense, quark plasma is beyond the standard model. To put it another way, the particle physics folks, they think of QCD in these proton-proton collisions as messy background that they're uninterested in. And what I'm trying to emphasize is that there's a lot of really interesting physics beyond the point particle interactions of, say, QCD or the Higgs particle.
So I have another thing about the smallest number that you can have. So incidentally, we have the same question when we're talking about flocking. You know,
I'm sure.
I just showed the picture of the concert there, but we tried to find what is the smallest school of fish.
Yeah,
makes sense. And so we had two guppies in a one-dimensional path, just swimming around, because then that's the smallest you can think. So why don't two? I don't see why.
So you can think about two,
right? No.
But it turns out that at least, where did I even have this? I think I had it earlier. Maybe it was. Sorry, I somehow don't have my cursor. Ah, perfect, found it. So here's two. And it turns out, with at least in the specific instance of cold lithium atoms, two is not enough. That two non-interacting lithium atoms. So if it's non-interacting, there's certainly no collective behavior that's going to happen. Two non-interacting lithium atoms and two very strongly interacting lithium atoms behave essentially the same. And the same thing is said about four lithium atoms. So the blue is completely non-interacting, and the red is very strongly interacting. They behave essentially the same. So there's nothing collective emerging. But six, at least for this particular lithium atom setup, they trap the lithium atoms in some kind of an anisotropic trap. They start with an isotropic momentum distribution, and then they release the trap and ask what happens. And if you have collective behavior, you should have this translation of the geometric anisotropy into a momentum anisotropy. And also, with time, an anisotropy of the coordinates because the momentum is greater from the pressure gradients. And that's exactly what they see. So I would love to get the reference for guppies. Yeah.
Well, it's still on the works. Again, the guppies may be more complex than a fundamental particle.
But this is what's very interesting, right? So similarly, you naively would think that the strong force is more complicated than the electromagnetic force. And so why would we try to understand the many-body dynamics of the strong force? Guppies are crazy. Compared to particle physics, guppies are infinitely more complicated. But if you think about the problem in the right way, in terms of the right degrees of freedom, perhaps, the problem becomes much simpler. And there are these potentially deep connections between something that is 10 to the minus 15 meters across and something that's 10 to the minus 1 meters across.
It's a bit fishy ending.
Not fishy at all. It's like nice Japanese fish from the store. It doesn't smell at all.
No. Just a small question. You had this plot where you had the entropy density against the temperature.
Yeah, I think this is a lattice QCD calculation. Yeah, here.
So the student increase is that roughly when the temperature is equal to the mass of your particle?
No. So
when Boltzmann suppression stops?
So what's happening here is, so what I mentioned that QCD has what's called a mass gap. What's incredible about that? If you look at the QCD Lagrangian, if you take the masses of the quarks to 0, it's completely conformal. There's no scale in the problem at all. And yet, a scale emerges. So you can talk about the proton mass, but really what's very important is what's known as lambda QCD. And that's this emergent scale from the conformal QCD Lagrangian that's of fundamental importance. And that lambda QCD is about 180 MeV. And that's what's dictating this transition here. That's what's setting this scale from normal nuclear matter of us to something else, which is quite clearly very dramatically different. Now you could ask, why 180? And nobody knows. And that's part of why it makes QCD very interesting.
Maybe one last question.
Yeah, great. Please.
I really like your idea of this numerical solution to this PD that you can also preserve this symmetry.
Yeah.
So, we mathematicians like to generalize as much as we can.
Yeah,
If
super.
I have a more general PDE, maybe wave type,
Sure,
and the coordinates that give us the preservation.
Yeah, let's talk. As I was preparing this talk, I was, asking ChatGPT what are sort of interesting questions. So there's like Berger's equation and obviously the wave equation, Euler's equation, Navier-Stokes, all of these. Yeah. So what is interesting to you? Let's talk.
Okay. Yeah, because I think it is probably also important to include some nonlinear terms, especially with recursive. Sure. Wave equation is linear, so.
We start simple.
Yeah, I know.
My postdoc supervisor said, little steps for little feet.
Okay.
And he had an equation named after him. So he definitely knew what he was talking about.
Very nice work. Yeah.
Thank you.
Okay, if there are no more questions, let's thank
Good luck.